Thank you very much for the introduction, and thank you very much for giving me the possibility of presenting this research activity concerning lightweight cement-based composites. So I will start with the motivation of this work, and then I will show you the results of some experimental tests on lightweight materials, and by using these results, I will propose you the use of the eco-mechanical analysis, which is a sort of approach in which we combine the material performances, the mechanical performances, with the environmental aspects. So we try to apply the concept of this eco-mechanical analysis to this particular case, to this case study. Here we are in the northwest of Italy, and this is a bridge, a very old bridge. It was built about 100 years ago. It's a double-deck bridge, and there is also a railway, especially in the bottom part. Anyway, the local administration would like to change something in this bridge, and in particular the sidewalks on the upper deck, transforming this deck from this situation to this one. In practice, they separated the people who are walking from them who are cycling here. So there is a problem in designing this slab on the deck, because below the slab there are some pipelines or something like that, and periodically you have to lift. They have to lift the slab for the maintenance. So, from the current situations made with the traditional concrete, they would like to do something lighter, so with a lightweight concrete, and in this way they reduced a lot the weight of the slab. So, lifting this slab is easier than the traditional situation, the current situation, and the question is, can we also remove traditional rebar and substituting this traditional rebar with plastic fibers? So we worked mainly on this aspect after changing the type of concrete. So we tested a particular lightweight concrete. It is on the market now, in the situation in which you don't have any fibers, and in another case in which they added 10 kilograms per cubic meter of these plastic fibers. We test the specimen in compression cylinders, and the full-scale tests were also performed on the slab. So here we have the tests in compression. The strength of the concrete is more or less the same, as you can see here, with and without fibers. As you can see in the post-peak behavior, the toughness is higher in the case of plastic fibers. But anyway, the slab is mainly in bending, so the evaluation of compressive strength just to check the class of concrete. In addition, as you can see here, this LC8 is the minimum strength that is required for this type of concrete. So in both the cases, we have higher strength than the minimum they require. a little bit higher is the strength in case of fibers, as you can see here, comparing the average values of this from the tests. We also analyzed the full-scale slab in 3-point bending, because this is the real structural configuration in service, because it is supported only on the two parts of the slab, and we concentrated the load in the middle. So as you can see, you have this behavior. The behavior without any reinforcement is really brittle. So after forming the crack, you have a softening like this. Also, in this structure, the load, the applied load, is lower than the strength of the material, the strength of the structure in particular. But anyway, the behavior is very brittle, so we need a reinforcement in this structure in order to provide a ductile behavior. So, in other words, in this structure, we need a minimum reinforcement. So, how can we define this the minimum reinforcement? According to the European standards, the minimum reinforcement should provide a cracking load equal to the ultimate load. Here you have, in the case of a 3-point bending beam, the behavior when you have plain concrete, like the one we tested before, without any reinforcement, so you have the brittle behavior. And if you add reinforcement, you can see after the crack the softening, but you have also this local hardening stage, which reach a maximum here, as you can see. But in this case, the maximum is lower than the cracking load. So we have to increase the reinforcement in order to increase this maximum and reach a situation in which the second peak, the ultimate load, is higher than the cracking load. This is, in general, the definition of the minimum reinforcement. So we have to provide a reinforcement in order to have these 2 points at the same value. In the case of the slab with traditional reinforcement, the minimum reinforcement is provided by code rules. So we have to provide, in this case, a reinforcement composed by 4 bars of 5 millimeter in diameter. And from this reinforcement, if we evaluate the moment curvature relationship, we can define the ratio between the ultimate deflection of the slab and the deflection at the end of the serviceability stage, or in general at yielding. And this is the so-called ductility ratio. We can evaluate also this amount of ductility provided by the reinforcement in this type of slab. In the case of fibers, the evaluation of ductility can be defined in accordance with the Model Code 2010, and in particular, the Model Code 2010 defines 2 points at the serviceability limit state and ultimate limit state. So the serviceability limit state is easily computed. It is a little bit more complicated to evaluate delta U at the end of the test. And in particular, we can define it by considering the distribution of the state of stress in the FRC like a plastic constant distribution at this value of the strength. So, in the slabs, if we had 10 kilograms of fibers, we can obtain a situation in which the cracking load is equal to the ultimate load, like in this case, and according to the model code, we can also define the ductility ratio as the ratio between the deflection at ultimate load and that at serviceability state. In this case, as you can see here, this value is very large. It's a huge value. So now we can, after performing the mechanical test, we can introduce a way to rate the mechanical performances in addition to the ecological aspects. And in particular, some years ago, we introduced this diagram. It's a non-dimensional diagram. On the horizontal axis, we have the ratio between the mechanical performances and the minimum value of these mechanical performances. On the contrary, on the vertical axis, we have the maximum impact of the concrete with respect to the impact that we have in the in the traditional in the concrete that we are analyzing. So the situation in which both these values are 1, so we are at the minimum and performance at the maximum impact is the reference point. So if we have a concrete which falls in this part, we have a situation in which both the mechanical performances and the ecological performance cannot be accepted or are lower than the reference one. In this situation, we improve the mechanical performances, but the ecological ones are lower than the minimum we expect. The third case is the best situation in which we can increase both the mechanical and the ecological performances. And the fourth case is a situation in which we improve the sustainability of concrete, but anyway, the strength or in general, the mechanical performances are lower. So in our case, we defined the carbon footprint for the cylinders, and these are defined by the, if you want, EPD, or you can obtain it by the database on carbon footprint, but it is related to the unit volume of the material, and this is the situation in which we are in the slab, where the unit volume is multiplied by the volume of the slab. And we consider the two possible mechanical indices, the strength of concrete and the ductility. The ductility because in both the cases the slab has the same ultimate limit state and cracking one. And so we performed the analysis with the minimum value of the mechanical index equal to the compressive strength of the reference concrete, the concrete with traditional rebar, and and we supposed to have the minimum, the maximum impact dose of concrete with traditional reinforcement. In the second situation, in the slabs, we consider the minimum value of the ductility ratio, that of the reinforced traditional rebar slab and the maximum of the same, the maximum impact of the same slab. So in both cases, we obtained more or less the same results. So when you use fibers, you improve the mechanical performances, both in compression and concerning also the ductility. But the impact is a little bit higher than the reference concrete. So in general, this diagram is used when you have several types, several situations. But anyway, it is also used to tailor a better concrete. For the current situations, we have to move this point in this third sector in both the cases. So how can we do it? If the traditional concrete with reinforcement remain the reference, so we can, for instance, reduce the content of cement in this fiber reinforced concrete, because if we reduce the content of cement, maybe we reduce the strength of concrete, but we are in a situation in which we can do this because the strength of concrete is higher than the minimum that we are expecting. And probably we also reduce the amount of reinforcement because we reduce the the cracking moment. So we can also reduce the content of fibers. So the next step of this work, this is an ongoing work, so we are at the first step of the analysis, is to tailor a new lightweight concrete with fibers in order to shift this point in the third sector. So I conclude, so we can use this traditional lightweight concrete in substitution of the normal concrete in the bridge, in the slabs of this bridge. But at the moment, we have to define a better situation in which, in addition to the lightweight concrete, we can also add the fiber reinforced concrete and eliminate also the traditional rebar. Thank you very much for your attention.